Hi again everybody. In the last video we implemented the matrix and also all the operations we're going to need with the matrices. So in this video we're going to implement the neural network. So let's start. N will be the number of layers. The vector size will hold the sizes for each particular layer in that order. We need to have a vector of the weight matrices and also the bias matrices, and then we need to have delta W and delta B. We're going to use that in the backpropagation when we're given a mini batch, as I have mentioned in the previous videos. We're given a mini batch and we're going to accumulate the deltas or the gradients in those delta W and delta B matrices, and then we're going to divide those values by the size of the mini batch. So you'll see. Okay, and something else we need is the learning rate. Okay, now we can go on and implement the constructors. SZ, of course, will be the vector of the sizes of the layers, and alpha is going to be the learning rate. So n is obviously the size of size. Size should be SZ. And now we need, since we have n layers, we need n-1 weight matrices and b-1 bias matrices, and also the delta W and delta B matrices should have the same sizes. Now we can go through all the weights and say weight I will be a matrix of size I rows and size I plus 1 columns, since it's between layer number I and layer number I plus 1. B will always have 1 row and size I plus 1 columns. Since B0, as you can see, since B0 is actually the bias matrix for L1. Same thing for the delta matrices. And we also want to randomize the weights and the biases. And let's not forget the learning rate, which is actually very important. Now the first thing we want to do is the feed forward function, which takes the input layer, goes through all these operations we mentioned earlier, and returns the output layer, the result of our neural network. So it's pretty simple. Matrix feed forward input. Okay, so we go through all layers, and as we said, first we multiply the current layer with the matrix of the weights. So we have input equals multiply input and WI. Next thing, we add the biases. So to this result we want to add the biases for the corresponding layer, and after that we run that through the sigmoid function. So we want to have sigmoid here, and that's pretty much everything. Now we just return the input, which is the output already. Now let's go to the backpropagation, which will be the most fun part. I'm going to explain briefly how this works. So I assume you have already read some stuff about it, but maybe it's not perfectly clear. So let's take a look at this. I'm giving you as an example a simple neural network with two layers. A1, A2 is the input layer, and A3, A4 is the output layer, which is produced by our neural network. And Y1, Y2 is the actual answer for the correct answer for this input. Okay, so let's take a look. We have W1, W2, W3, W4 as the weight matrix between those layers, and B1, B2 as the biases for this layer. So let's see how. Oh, I forgot to mention the cost function, which actually tells us how close we are to how close our output A3, A4 is to the desired output Y1, Y2. So on the right, you can see here the cost function, which takes A, which is our output, our suggested output, and Y, which is the answer, and we're going to use the quadratic cost function, which is A minus Y squared. So obviously, as you probably know from high school, the derivative of this function, to find it, we simply take that power of 2, move it to the front of the equation as a coefficient, so it becomes 2 times A minus Y, and we decrease that power, which becomes 1. So that's the actual derivative, 2 times A minus 2 times Y. And I'm going to ignore that 2 here, since it's pretty much the same if we use a learning rate which is twice as huge, so it doesn't really matter. Now let's see how A3 is computed. So of course we have the activation function, and I'm using F instead of the sigmoid, but I mean the sigmoid because I don't have that character on my keyboard and I don't want to copy it every single time. So F is actually the sigmoid function. So A3 is sigmoid of A1 times W1 plus A2 times W3 plus the bias B1. So that's A3. A4 is A1 times W2 plus A2 times W4 plus B2. And of course the sigmoid of that. So that's A4, that's how we get A4. Now let's take a look at the cost functions we have for Y1. The cost function at this cell, Y1, is the cost function with arguments A3 and Y1. The cost function at this cell is the cost function with arguments A4 and Y2. So let's write this down. We simply replace A3 with this here. Okay, I've put that in blue so you can see that easily. And we replace A4 here. So yeah, now we're going to see how to find the partial derivatives with respect to the biases and the partial derivatives with respect to the weights. So let's start with B1. Okay, B1. We want to see what's on the outermost layer. That's the cost function, okay? Something here squared. So it's actually the cost function taken with A3 and Y1 squared. So yeah, just the cost function. So first we take its derivative, the derivative of the cost function with arguments A3 and Y1. Then what's the next outermost layer? It's the F function, which is the sigmoid function. So we multiply that by the derivative of F at A3. So that's pretty much the partial derivative of the cost function with respect to B1. Now with respect to B2, let's take a look at B2. The outermost layer again is the cost function. It's right here. Cost function with arguments A4 and Y2 this time. Then the next layer is the F function taken from A4. So we just multiply that by A4. Now let's take a look at W1, which is right here. The outermost layer is again the cost function with arguments A3 and Y1. So we first take the derivative with a3, the derivative of the cost function with arguments a3 and y1. Then the next layer we have is again the f function at a3. So we multiply that by the derivative of the sigmoid function at a3. And then we have a coefficient in front of w1, which is actually a1. So we multiply that by a1. And that's the partial derivative with respect to w1. Take a look at w2 now. The outermost layer, again, the cost function with a4 and a4 and y2. So we take that derivative first. Then the next layer is the sigmoid function taken at a4. So we multiply that by the derivative of the sigmoid function at a4, and then we have a coefficient in front of w2, which is equal to a1, so we multiply the whole thing by a1, and that's the partial derivative with respect to w2. Take a look at w3 now. Okay, w3 is right here. Outermost layer, cost function. Next layer, sigmoid function at a3. And then the coefficient in front of w3, which is a2. So that's the partial derivative with respect to w3. And now w4, once again, first we have the cost function with a4 and y2 as arguments. Then we have the sigmoid function at a4. And then we have the coefficient in front of w4, which is a2. So that's pretty much what we're gonna do. We just have to implement it. So let's go on. First of all, I want to have a vector which will actually save those values of the layers as we go. So the first layer, L0, which is the input, is of course the input. Now we go just like in the feed forward function. We say input equals sigmoid of add of multiply input wi bi. So pretty much the same thing. And then we push that in the L vector. So yeah, we have now calculated those L values. I want to have a matrix delta, which will help us store the current derivatives. As you see, we will keep appending some factors here to this product. So yeah, that's how we're going to do it. The first thing we want to do is to find the biases for the last layer. As we said, here you can see, we first have to take the cost derivative, which is actually a minus y. So we first say delta equals subtract input and output, and don't forget that input is now the output of our neural network and output is the actually desired answer, the correct answer. So we first want to subtract input from output, and that's going to be our cost derivative here. And then, okay, you see that's just term by term, the cost between a3 and y1, and then a4 and y2. And then we want to multiply those things by the sigmoid derivative of the last layer. So we have delta equals term by term multiplication of the current delta and the sigmoid derivative of the last layer, which is Ln minus 1. Yeah, we have n layers. So I'm simply going to take this row here, subtract input output, and put it right here. So once again, we first take the cost derivative, which is just the subtraction. Then we multiply that vector by the vector of sigmoid derivatives of the last layer. So that's everything. And we can say that this is actually the gradients, the partial derivatives with respect to the biases of the last layer. So as I said earlier, in delta W and delta B, we're going to accumulate those values. So I'm going to say delta B n minus 2 dot add delta. Okay. It pretty much says, okay, those are the gradients for this example, go accumulate them. And then we're going to divide that by the size of the mini batch. So delta B n minus 2, that's the last layer of biases, dot add delta. Now, let's see what we're gonna do about the derivatives with respect to W. Well, you can see here, W1, W2, W3, W4, they're actually pretty much the same as those partial derivatives, like the partial derivatives with respect to the bias. The only thing they have additional is that W1 and W2, you can see W1, W2, have this A1 factor here in front of them, and W3 and W4, here they are, have this A2 factor in front of them, or after them, doesn't really matter. So we simply want to transpose this layer, which is not the last, but the one before that. We want to transpose that layer and multiply it by delta. So that's pretty much everything. Not n2, but yeah, n minus 2, not n minus 1. Anyway, now we can simply go through all the layers and do the same thing. Now, after we have went to this layer, we have to, like, you know, this layer was produced by first multiplying this layer by the weight matrix. So we now have to inverse that and multiply it. We have to multiply delta with the transpose of that weight matrix. So we're actually going a step backwards. And now we do pretty much the same thing as we did here. The current delta becomes the term by term multiplication of the current delta, and the sigmoid derivative of layer I plus 1. Then we say delta B I dot add delta, and delta W I dot add multiply of transpose Li and delta. So that's pretty much the back propagation. And now we want to have the train function, which actually gives us the mini batch. It gives us a lot of inputs and their corresponding outputs. And all we have to do is first set those delta matrices to 0, since we're going to be accumulating the gradients there. Then we're going through all examples, and we're calling the backpropagation function with all of them. Okay. This helps us accumulate all gradients. And now the final step is simply to divide those delta values delta Wijz is divided by the size of the mini batch, and then subtract this gradient from the current weight. This is our modification, and let's not forget that we have to multiply this by the learning rate, since it tells us how fast we want to be learning. And now we do the same thing for the biases. This delta bi dot n is always 1, but I'll just write it this way. Once again, the current delta is divided by the size of the mini batch, and then we make the small change to that bias. So this has to be everything. Let's see if it will compile successfully. Okay, it actually does. So this is all for this is everything for this video. In the next one, we're going to download the dataset, and we're going to make that neural network learn from the training set. And yeah, that's going to be everything. We just have to submit the answer after that. So see you in the next video.